Hi, in this video I will be demonstrating the difference between conventional pigment and graphene pigments. So what we are seeing here are the very simplistic models showing the cross-sectional view of a coating on a metal surface. Metals such as iron and steel are coated with polymer or plastic paints to prevent them from corrosion. The paint or the coating acts as a barrier to moisture and oxygen present in the atmosphere. So moisture or water molecules and the oxygen are agents of corrosion, and they cause corrosion of metals. So how do they cause corrosion? Oxygen present in the atmosphere oxidizes metal to metal oxide. For example, iron is oxidized by oxygen to iron oxide, and this oxide reacts further with moisture present in the atmosphere to form hydrated iron oxide, which is nothing but rust. For corrosion to occur, both the water molecule or the moisture and oxygen from air should be present simultaneously. If either of the two are absent, corrosion of metal will not occur. Now, what we also see here are these small structures. So what these represent pigment particles in a coating, and the empty space represents the matrix in which the pigments are dispersed. Most of the anti-corrosion paint will have 20 to 40% by volume of pigments. Pigments perform a variety of roles. Basically, they are powdered solid particles which are dispersed in the paint. A pigment in a paint will perform several functions. Colored pigments, they provide color to the coating. Extenders are added to give volume to the paint so that we minimize the use of the polymer or the resin, which is also called the binder. So resin or binder are more expensive than the extenders. So if we can use more extender to increase the volume, we are actually reducing the cost of the paint. Other than that, extenders also improve mechanical properties like toughness in a paint. Anti-corrosion pigments improve the corrosion resistance property of a coating. They can be active or passive. As the name suggests, active anti-corrosion pigments provide protection by certain chemical reactions. Passive anti-corrosion pigments, on the other hand, provide protection against corrosion, usually by acting as a barrier to the oxygen and the moisture. So they enhance the barrier property of a coating. Shortly, we will see how the passive anti-corrosion pigments restrict the flow of water molecules and the oxygen molecules or air molecules through the coating. My main objective of this demonstration is to showcase the difference between conventional pigment and graphene-like pigments. So planar, flat pigments having high surface area. So planar pigments like graphene and other 2D materials like boron nitride, they are believed to provide very good barrier to oxygen and water molecules. Generally, it is quite difficult to visualize how planar flat structures like graphene will improve the barrier property of a coating as compared to the conventional pigments. Hopefully, by the end of this demonstration, it will become more clear. We will see how planar pigments, we will see how planar pigments help in providing tortuous pathway to the molecules, thereby increasing the amount of time it will take for the molecules to cross the coating. So let's start with the demonstration. So we have got the graphene type pigment and we have got the conventional pigments. And I have these spherical balls here which represent the water or the oxygen molecules. So we will consider, for the sake of this video, that these are the molecules. So let's see what happens when I drop these spheres from the top here. So we saw how much extra time it took this sphere to come down all the way from the top in this case, and in the graphene type flat pigment case. Now let's try with the more spheres. So we have a few spheres here, and I will do the same. Drop these molecules from the top. Whoa! Let's do it once more. Do we get similar results? Alright, so what did we see? We saw it took more time for the spheres or molecules, let's say molecules, to cross the coating from top to the bottom to reach the metal surface at the bottom. So we have effectively increased the diffusion time of molecules by using flat planar structures. Now, at least by looking at this demonstration, we can say that the planar pigments like graphene are really effective in providing barrier to the coating in comparison to conventional pigments. Now a question arises, one might be thinking, okay, although it took more time for the molecules, let's say, to reach from the top of the coating to the bottom to reach the metal surface, eventually the molecules will reach the metal surface and they will corrode the metals. However, in reality, that is not the case. Absorption of molecules, water and oxygen on the surface of the coating and desorption occur simultaneously. So these two processes are in equilibrium generally. The rate of desorption will depend upon the concentration of molecules on the surface of the coating. If somehow we can slow down the movement of molecules through the coating, we will have more molecules on the surface of the coating for desorption, and hence we can increase the rate of desorption. That is why slowing the diffusion of molecules through the coating by providing suitable barrier is so important. But how do we know the coating is really intact, that it has not absorbed too much moisture into it? Well, we can actually prove it by calculating the impedance of the coating through an instrument called electrochemical impedance spectroscopy. So as the coating absorbs moisture, its impedance goes down, and if the moisture or the water molecule is able to reach the surface of the metal through the coating, then the impedance drops down significantly and the coating behaves almost as a conductor. So by calculating the impedance, we can prove that the coating has not absorbed too much moisture. To make graphene as an effective barrier pigment, few things seem to be critical. First, the particle size of graphene pigments. Particle size affects orientation and arrangement of the planar pigments, which could be very important to the barrier effect as we saw in the demonstration. A very high particle size may introduce defects into the coating. The reason for this is that the particles larger than the thickness of the coating will provide easy pathway for agents of corrosion to reach the metal surface. The interface between the polymer and the pigments have completely different properties than the bulk of the material and are places of weak intermolecular forces. As a result, interfaces, if exposed above the coating surface, can be easily attacked by water and air molecules, and if these particles are larger than the coating thickness, then they will provide low hindrance to the passage of corrosion initiating molecules. A low particle size of the pigment will not be effective in providing enough barrier to restrict the flow of air and water molecules as we saw in the demonstration. Low particle size also means more particle agglomeration as they have got high surface area and hence high surface energy and therefore unstable. Smaller particles as a result will also diffuse quickly and form agglomerates and aggregates. They will do this to reduce the surface area. Second factor which affects the barrier property is the quantity of particles. A lower quantity of particle may not have a very huge impact on the coating's performance, but a high amount of pigment then the optimal value will hinder polymer network formation and therefore reduce the inherent mechanical properties of the coating, including the natural barrier property of the resin, which is inherently found in the polymer in the absence of any pigment particles. There is yet another factor which is very important for the corrosion resistance property of a coating, and that is the adhesion of the coating to the metal substrate. A coating can be very good barrier, but at the same time it must have a good adhesion to the substrate. This is particularly necessary to prevent the spread of corrosion around the damaged area of a coating. As we all know, coatings undergo a variety of mechanical stress such as erosion, abrasion, impact stress, as well as thermal stress. All these stresses have the potential to damage the coating and expose the metal substrate. Coatings in harsh environment are highly likely to get damaged due to mechanical and thermal stresses. Around these damaged areas, the barrier property of the coating will have little effect in stopping the corrosion of the metal. As the coating experiences mechanical and thermal stresses, there is a chance for it to get detached from the metal substrate around the damaged area. Once a coating is detached around the damaged area, water and air molecules can creep underneath the coating and initiate corrosion. As a result, iron is converted to rust. Coatings have very poor adhesion on rust and therefore get detached around the damaged area more. If the coating is thick or has good barrier properties, the level of stress within the coating increases. Also, the creeped water and air molecules find themselves entrapped underneath the excellent barrier of the coating, which causes excessive corrosion beneath the coating. This problem can be addressed by improving adhesion or increasing the flexibility of the coating. A flexible coating experiences much less overall stress as it gets distributed evenly across the coating, thereby protecting the coating from disbonding from substrate. However, care must be taken when increasing the flexibility because it may reduce the barrier property of the coating.